Okay, thank you for the introduction. And right, so let's begin. So just as a color coding on this slide, in this kind of field, there are lots of technical details that you might not want to have to discuss all the time. So some things are highlighted in gray, and those are just on the slide so that I'm not putting lies on the slides. And maybe if you're just trying to understand it, they're okay to ignore. And some other things are in orange. And what that means is that's sort of an important detail for the talk, but it's not something that I have much time to go over. So a lot of you will know the orange already, but if you don't, it's maybe something that's good to look up afterwards. So just as an outline, I'm going to start by just defining and motivating what a quaternionic automorphic representation on G2 is. After that, I'm going to give some background on trace formulas and why they're sort of the right tool to attack this problem of understanding these quaternionic automorphic representations. Then I'm going to talk about the specific simple trace formula that makes this a tractable problem. And then I'm going to go over some details of the exact computation, specifically what happens on the spectral side and what difficulties come up there, and then what happens on the geometric side and what difficulties come up there. And the details are all on archive, and it's a pretty short thing, so it's not too bad. So let's start. So what is a quaternionic automorphic representation on G2? So one way to motivate the story is you can ask a question. There are all these forms on classical groups and other kinds of groups that people knew about way back when. So you might want to think about whether, now that we have all this general theory, whether we can find examples of automorphic representations that correspond to some nice simple forms that maybe people didn't know about classically. So if you want to find something that people didn't know about classically, exceptional groups are a good place to look. And you don't want to just pick a random automorphic representation. You want to pick an automorphic representation with a nice component at infinity. So you want to look at something that's an analog of modular forms, not an analog of mass forms. So the component at infinity, so it gives you a lot of qualitative properties of the automorphic representation. And you want to pick some nice kinds of discrete series at infinity so that the automorphic representations and the forms that you get from them are nice in the same ways. So the simplest example that you can think of when you go through this thought process is that you might want to look at G equals G2, and then pi infinity, the infinite component of your automorphic representations, will be something called a quaternionic discrete series. So what does quaternionic mean? Quaternionic, basically it means that there's a nice differential equation condition on the functions that make up the representation. And this differential equation condition is a second best condition to the functions being holomorphic. It sort of has to do with the minimal k type of these representations, the real representations being as simple as possible. And discrete series are just the real representations that live discretely inside L2. And the relevance for us here is that the discrete series is going to make these representations studyable using the trace formula, without more easily studyable using the trace formula. So since we're talking about these quaternionic discrete series, just for now, let's just say that there's one that we're going to call pi sub k for every weight k that's greater than or equal to 2. That's what quaternionic discrete series are. Why might we care about them besides just this motivation? So they come up in certain situations. There may be 2 so far. So first of all, Fourier coefficients of these quaternionic discrete series, they encode interesting arithmetic information about cubic rings. And this was a paper of Gangros and Savin. And second, and this is a little bit stranger, but there's certain computations in string theory, and there's a book that talks about how these computations relate to automorphic representations. And sometimes you get things that look like quaternionic discrete series on G2 when you do these computations. So these are sort of a reasonable small example. So hopefully there'll be many more of these kinds of applications in the future. So that might be why you care about them. What exact question are we going to look at? So maybe a first question we can ask is, how do we describe quaternionic discrete series or quaternionic G2 automorphic representations? And maybe an example of how we can describe, maybe we can ask the simplest possible question, can we count them with some local conditions? So this counting problem, this description is what we're going to focus on. Okay, so that was the introduction, quaternionic discrete series. Now let's discuss maybe the results, what answers to these questions we have. So it turns out that both these questions can be answered without much trouble when you restrict to level 1. So what does level 1 mean? Level 1 means that the away from infinite component of the automorphic representation has a subspace that's fixed by a product of hyperspecials at each of the away from infinity places. And the subspace is necessarily going to be one-dimensional. And the answer is not going to be a direct answer, but it's going to be in terms of things happening on this compact form of G2. So what is this compact form? Well, it's isomorphic to G2 at all finite places, and it's going to be compact at infinity. So in particular, we can talk about the z points of this compact form. So just as some notation now to describe the results later, just let V sub lambda be the finite dimensional representation of this, the real points of the compact form with highest weight lambda. So it's going to have some matrix coefficients that live inside L2 because this is the compact form. So we can think of it as made up of functions on this on L2. And then we're just going to let beta be the highest root of G2. So here's the result. So let k be greater than or equal to 2. The number of discrete level 1 quaternionic automorphic representations on G2 of weight k is the dimension of, well, okay, I guess that should say fixed points instead of restriction, but the dimension of the G2 compact Z fixed points in this finite dimensional representation, plus this sort of correction term over here. So yeah, this is a reasonably explicit formula. This term over here might look a little bit scary, but actually there's an undergraduate thesis by one of Gordon Savin's students that gives us as sort of a sum of maybe 16 explicit polynomials that are like, these are cases mod 12 and those polynomials are cases mod 7 or mod 12. So this is also a very explicit thing. If you write it all out, you can probably get this entire formula as like something that can fit on a piece of paper.
Level 1 quaternionic ones can be seen by algebraic modular forms.
No, because there's this correction term down here. Right, so the algebraic modular forms will be this dimension over here of the fixed points. But there's also this correction over here. So the next slide will go over that a little bit more. Right. So yeah, so there's this algebraic modular forms place, and then there's this correction. And if you remember sort of your very classical, like first learning about modular forms thing, these floors of fractions divided by 12 should look a little bit suspicious because these look kind of like dimension formulas for classical modular forms. And in fact, that's what's going on here. This correction term comes from classical modular forms. So we don't just have a dimension formula, we have a description of all the level 1 quaternionic automorphic representations. So let k be greater than 2. If k is even, the discrete level 1 weight k quaternionic representations of G2 are exactly the unramified ones with the correct infinite component and Satake parameters that come from the weight k minus 2 times beta algebraic modular forms on compact G2. And then there's a correction in addition to the things with Satake parameters that come from pairs of classical classical modular forms in weight k minus 2 and then weight 3k minus 2 and weight k minus 2. And if k is odd, it's a very similar description. You get the algebraic modular forms on compact G2, but then it's instead of an addition to, it's except for the ones coming from a different pair of classical modular forms. Okay. So are there any questions on this result? This is maybe the most general result that I'll be discussing. Okay. So just so you can see, here's just a table of what these dimensions are in terms of this weight k. And sort of the interesting point here is that weight 6 is the first time you find one. So I'm just going to warn here that this is it only works for k greater than or equal to 2. And just by this, you don't know that there isn't anything of weight 2, but it's probably very unlikely that there'll be something of weight 2, just because like these things need classical modular forms, you need to go up to weight 12 before you find anything. So there really shouldn't be anything there. And there might be another argument that's not very difficult that I'm just not aware of that eliminates the weight 2 possibility. Okay, so those are our results. Are there any questions? Yeah.
These guys, are they cohomological, these quaternionic ones? And they appear in the cohomology of some arithmetic quotient?
Yeah, so the infinite component is cohomological, so I think that means that it should, right?
It's discrete, yeah.
Yeah, it's discrete series at infinity. Yeah.
The group is compact, right? At infinity.
The other group is compact at infinity, so we're describing it in terms of the group that's compact at infinity.
Discrete series is always compact.
Yeah.
Maybe a unique group compact at infinity?
Yeah, there's a unique one that's compact at infinity. Yeah. Just because it's like at the p-adic places, there are no inner forms and there are no outer forms because of the diagram. Okay, so now let's talk about how we might produce this result. So we'll start sort of very basic. So automorphic representations, they're sub-representations of some specific L2 space. So you want to study the decomposition of a big representation into sub-representations. The first trick you learn is you look at traces. So we're going to assume for a moment that this L2 space decomposes as a direct sum of discrete automorphic representations. Then we can pick some operator on this L2 space. And we know that the trace against the entire L2 space is going to be the sum against the components of the trace against each of those components. So where do we get these operators? Well, there's a good source of them by looking at convolution operators. So if we pick some nice enough function on G of the Adels, then we can define this sort of average translation operator. And by picking clever Fs, we're going to get a wide variety of different Rs. And by choosing the right R, then we might be able to probe lots of different information about which exact automorphic representations exist and which don't. So that's our general strategy. Here's our specific example. So what we want to find is we want to find an F such that trace against L2 of F is the number of G2 quaternionic level 1 weight K automorphic representations. So our idea, what we want to do, we write this F as a product of an F at each place. And then the trace is going to be the product of the local components of the local test functions. So what we have to do is we have to find an F infinity such that trace of pi infinity against F infinity is just going to be an indicator function, whether pi infinity is the thing we want it to be, this weight K quaternionic discrete series. And then if K of away from infinity is a maximal compact and G2 away from infinity, we just note that the trace against pi away from infinity of this indicator function is just the volume times an indicator function, whether it's in ramified, right? Because that subspace was necessarily one-dimensional if it exists. So this is just some elementary computation once you plug that in. So this is the test function we're going to use. We're going to find this F away at infinity, and we're just going to use this F at infinity times this indicator function of this hyperspecial. So that's our test function. Now we know what trace we want to compute. How do we actually compute that trace? So we're going to use something called the Eichler-Selberg trace formula. So what is the Eichler-Selberg trace formula? Well, it's a sum. We're interested in the spectral side, which is just a sum over all automorphic representations of the multiplicity of how many copies of it live in the space times the trace against pi of this. So this is what we're interested in. And that's called the spectral side. Then there's a geometric side in orange, and this is what we're going to try to compute. Okay, so this geometric side, just think about it as there's a sum over rational conjugacy classes. There's some volume terms of adelic quotients of centralizers of these rational conjugacy classes. And then there's an integral over the conjugation orbit of the rational conjugacy class. So this is the general framework. And of course, well, this isn't approximately equal. So the real thing is a lot more complicated than this. But in our specific case, when our infinite component is a discrete series, this approximately equals can become an exact equality with a few extra corrections that aren't too bad. Okay, so at this point, I think I should say a little bit more about details about what discrete series are and how they're classified and which exact discrete series we're going to be looking at, which ones are the quaternionic ones on G2. So just as maybe this is a reminder for most people, but discrete series are the representations that appear discretely in this L2 space on the real group. They're classified into L packets that I'm just going to say pi sub lambda. And these L packets, they're parameterized by dominant weights inside dominant weights lambda. And the way you do it is the pi sub lambda goes to discrete series with infinitesimal character lambda plus rho. So we say that the L packet is regular and the discrete series are regular when lambda is. So when the infinitesimal character minus rho is regular. And within each specific pi lambda, the representations within it are parameterized by maximal compact dominant Weil translates of the infinitesimal character. And we call this the Harish-Chandra parameter of the discrete series. So yeah, for G2, maximal compact has like a Weil group of size 4. So the G2 has a Weil group of size 12. So there are 3 representations inside each L packet. Okay. So which ones are the quaternionic ones? Well, they live inside the L packet, k minus 2 times the highest root, the weight k1. And it's the one that has a Harish-Chandra parameter that's in a chamber that's adjacent to the long compact root. So the maximal compact for G2 is an SU2 times an SU2 made by one long root and one short root that are perpendicular to each other. And you take the chamber out of the 3 that's adjacent to the long one. And the other way to say this is that the minimal K type of the quaternionic discrete series is trivial on one of the SU2 factors. So this is the thing before that they have the simplest possible minimal K type, and that is what leads to all their nice properties. Okay, so that's a specific discrete series we're looking at. Let's state this trace formula. So if G over F is some reductive group and we pick a regular discrete series L packet, then we look at the set of all automorphic representations of G with the infinite component inside that L packet, and we pick some test function away from infinity. Then there's this explicit formula for the sum over all those representations of the trace away from infinity. So this formula might look a little bit complicated, but it's very explicit up to these orbital integrals. And it's very similar to what I was showing before. So it breaks up into the same kind of 3 pieces. There's a sum over conjugacy classes. There's a volume term. And then there's something that's like an orbital integral that's factored into some part at infinity and a part away from infinity. So this is the trace formula that we're going to use that makes this problem a tractable problem and makes you actually able to probe the spectrum and get counts. Okay, so how does this work? This trace formula works by plugging in a specific test function at infinity. So discrete series pi, they come attached with functions called pseudo-coefficients that I'm going to denote by phi pi. So what a pseudo-coefficient, how it's defined is that for all standard modules, the trace against the standard module of the phi pi is going to tell you exactly whether that standard module is a discrete series or not. So the key point here is that this fact only works for standard modules, not for irreducible modules. So it's a little bit more complicated than just what a matrix coefficient would be. It's a pseudo coefficient. So what we can do is we can average these pseudo coefficients over an L packet, and we get something called an Euler-Poincare function. And then these Euler-Poincare functions have a property that for lambda regular and rho any unitary irreducible representation, the trace against rho of this Euler-Poincare function is going to tell you exactly whether the rho, there should be a rho here, whether that rho lives inside the L packet or not. So to get the simple trace formula, what you do is you plug in an Euler-Poincare function as an infinite component of your test function. And well, sort of this property by itself, plus some facts about Arthur's invariant trace formula on the spectral side, computes the spectral side. And the geometric side requires a bunch of work, and that's the content of the paper, of that Arthur paper. Okay, so we have this great trace formula that lets us compute stuff explicitly when we're looking at automorphic representations with discrete series at infinity. However, if you were paying attention, there are a few problems applying this to our specific case. So it doesn't quite work for what we want to do. So the first problem is this trace formula. It'll count all representations with the infinite component inside the entire L packet instead of infinite component exactly equal to the quaternionic representation. So the solution is that we want to plug in a pseudo coefficient at infinity instead of an Euler-Poincare function, because a pseudo coefficient tells a specific discrete series, the Euler-Poincare picks out the entire packet. But the problem then is that Arthur's work for simplifying the geometric side, it doesn't really apply anymore. So the geometric side doesn't simplify nicely then. But it turns out that you can use some techniques of stabilization to resolve this issue. The next problem is that this lambda, this k minus 2 times beta, is not regular. It's on the wall of the Weil chamber. So the spectral side may not actually simplify nicely when you use an Euler-Poincare function or a pseudo coefficient that's irregular. But this actually doesn't matter because there's some facts from real representation theory that'll tell us that this is not an issue specifically for quaternionic representations. Finally, the terms on the geometric side, they might be explicit, but they're very tedious and difficult to compute. In particular, these orbital integrals, they take a lot of work to actually compute out. So there's some tricks of Chenevier and Renard that apply to a level 1 that let us avoid having to do a lot of work on the geometric side and actually just use spectral side calculations on smaller groups where they're already known. Okay, so the rest of the talk is just going to be going over the details of how to resolve each of these 3 problems. Are there any questions at this point? Okay, so let's start with problem 2, or problem 1 and 2 sort of, well, okay, let's start with problem 2. So this is what's going on at the spectral side. So this is what we want. What we want is that if we have f infinity, a compactly supported smooth test function away from infinity, then for any work weight k greater than 2, the spectral side of this invariant trace formula is going to simplify in this way. Then we plug in a pseudo coefficient at infinity, we get the sum over automorphic representations with that component at infinity times this trace away from infinity. So we can do some quick simplifications with some properties of Arthur's trace formula. The pseudo coefficient satisfies the technical property of being cuspidal. So the spectral side is going to simplify as a sum over discrete automorphic representations of this trace at infinity times this trace away from infinity. So our problem basically reduces to if sigma is an arbitrary unitary representation of the real group and weight k greater than 2, it has the infinitesimal character k minus 2 times beta plus rho. Then the trace against sigma of this pseudo coefficient needs to exactly pick this out. So we need this for all unitary irreducible representations instead of just standard modules now. So this is what we're going to have to show. Okay, are there any questions? Okay, so that was the trace formula work. And now it just, all we have to do is some work with the real representation theory and figure out how to figure out traces against unitary representations from the traces against standard modules. So one fact that I'm just going to say here is that it suffices to check this on cohomological representations of the correct weight. And these are representations that are classified by Vogin and Zuckerman. So maybe these days, the fastest way to see this fact is that there's a theorem that any unitary representation with this sort of infinitesimal character is going to be cohomological. But there are less high-powered ways to see this. Okay, so you look at this classification of cohomological representations, and it turns out that if k is greater than 2, and this is where that condition k greater than 2 comes from everywhere, there's only one non-discrete series cohomological representation of weight k minus 2 times beta. And we're just going to call that pi bad. right? So discrete series are all standard modules by themselves. So we know that the trace against a discrete series of the pseudo coefficient is going to tell us exactly whether this discrete series is the exact one we want. But now we just have to check that the trace against pi bad of the pseudo coefficient is 0. So how do we do this? Well, okay, so Adams-Johnson and sort of the paper that constructed the Adams-Johnson packets, they state a way to compute the expansion of pi bad in terms of standard modules in the growth and D group. And what we have to do is show that the discrete series doesn't appear in that expansion, the quaternionic discrete series. And there's an explicit formula for this, but it's in terms of some like things called cohomological continuations that are a little bit of work to compute. But actually, well, Sam Mundy did all this work, and he sort of stated it in a different way for different purposes, but we can just bootstrap off that and avoid having to do this. So the fact that we're going to use is that pi bad, it corresponds to an A packet, and the A packet is just 2 representations, which is pi bad and the quaternionic discrete series. Next, there's a lemma in this Adams-Johnson paper that defines the Adams-Johnson packets, that a given discrete series is only going to appear in the growth and D group expansion in terms of standard modules of exactly one member of the A packet. So it appears in the growth and D group expansion of itself, just trivially, because it's a standard module. So it can't appear in the growth and D group expansion of pi bad. So therefore, you immediately get that the trace against pi bad of the pseudo coefficient is 0. So I just want to make a note here that by slightly more complicated arguments, there's some combinatorics about exactly which of these cohomological representations exist and which ones can exist with certain Harish-Chandra parameters. And you can look at this combinatorics and it sort of lines up very nicely with the combinatorics that makes a discrete series quaternionic. And you seem to be able to show that this kind of coincidence, that the pseudo coefficient picks out exactly the discrete series and no other non-tempered representations, that works for every quaternionic discrete series on any group. So I haven't written this up, so there could be something wrong with it, but this should be true. So it's not just a G2 specific thing, it's about it being quaternionic. Okay, so this resolves problem 2. The spectral side all works out. We can sub in the pseudo coefficient inside of the Euler-Poincare function. We don't care that the weight is non-regular. We can still get our counts. Okay, are there any questions?
You mean Grotini group expansion, writing a representation as a sum of standard modes?
Yeah, exactly. Yeah, it's a thing that people call character formulas when you, yeah. Okay, so now let's talk about problem 1, the first problem, the problem that the geometric side doesn't simplify with pseudo coefficients. So the tool that we're going to use to deal with this is stabilization and the stabilization of the trace formula. So let me just give a very quick introduction to what this is, sort of focus on what's relevant for this problem. So basically what happens is that a trace formula with these, if you remember the formula that I gave before, the Arthur simple trace formula, all the terms there are invariant under conjugation. But that's not good enough for a lot of applications. What we need is we need something called stably invariant terms instead. And what that sort of means is that they're not just invariant under conjugation of G of the group, they're invariant of the conjugation over G of the algebraic closure. So like you can think about SL2 with like if you have like an elliptic conjugacy class in SL2, it may be like with the characteristic polynomial, there are like 2 conjugacy classes over R, but there's only 1 over C. And these terms might only be invariant over R conjugacy, but you actually want terms that are invariant over C conjugacy. And for lots of purposes, this is super useful. In particular, these stable conjugacy classes are much easier to parameterize. There's a generalization of characteristic polynomials. But for our purposes, it sort of lets us swap between the Euler-Poincare functions and the pseudo coefficients. So how do we get an expansion in terms of these stably invariant terms? Well, so I'm just going to state giant black boxes right now. So G has associated to it some groups called elliptic endoscopic groups H. And there's a definition if you care about them. It's something that's explicitly described and you can compute them out in terms of root data and some minor work with cohomology. If you have a function on G, then you sort of get a transfer function on H. This is, I mean, maybe it's not like perfectly well defined, but just for our purposes, it's just, there's just a transfer function on H. And it's defined by some kind of identity on orbital integrals where some kind of like linear combination with the non-constant signs of the orbital integrals in a stable conjugacy class equals the stable orbital integral on H. And then there's this expansion that for some distributions that are made up of stable invariant terms called S, you can write I as a sum over these elliptic endoscopic groups of that distribution for the endoscopic group of the transfer. So again, we're not going to have to worry about too many details of exactly what's going on here and what S is or anything like that. We just need to worry that it changes this F to something that you plug into a stable distribution. Yeah, so how is this going to help us compute I geometric? So we'll recall that this I geometric of F away from infinity, F at infinity, it simplifies if F at infinity is a linear combination of Euler-Poincare functions. That's a big part of the content of the Arthur paper. So what we might want to do is we might want to write I geometric with the pseudo coefficient as a linear combination of I geometric with these Euler-Poincare functions. And here's a lemma. So if the pseudo coefficient actually has the same stable orbital integrals as an Euler-Poincare function. Furthermore, all endoscopic transfers of pseudo coefficients can be taken to be linear combinations of Euler-Poincare functions. So basically, when you do this kind of stabilization, all the terms on the other side end up being things where you can have Euler-Poincare functions at infinity. And you can play around with this a bit, move things between sides of the equations. And basically what ends up happening is that stabilization lets you write the geometric side with the pseudo coefficient as a linear combination of geometric sides with Euler-Poincare functions on these smaller endoscopic groups. And that's sort of the key point here. So what exactly are we going to do? Let's just recall that our test function looks like this. There are two sort of key computations that you have to do. One computation is that for a test function like this, all the terms for endoscopic groups, all the transverse endoscopic groups are going to vanish, except for one specific group, SL2 cross SL2 mod plus or minus 1. Basically what happens is because we're unramified away from infinity, you can't have any groups that are non-split, where the transfer doesn't vanish. And because it's a discrete series, the pseudo coefficient at infinity, every group where the transfer doesn't vanish needs to have discrete series. So those two conditions make sure that there's only one extra term that comes up. Then you get that this S applied to the SH for this specific H actually equals IH. And this is the part where it's very important that you're unramified, because this H has further endoscopic groups that might come up in your expansion, but they die away because they're non-split. So after this, we can apply a certain trick that we're going to look at this compact form of G2 again, and we're going to note that the transfer of the Euler-Poincare function from the compact form to the split form is just an Euler-Poincare function. This Euler-Poincare function on the compact form is nothing complicated. It's just a matrix coefficient of the finite dimensional representation. And then you can just play around, just do some like very quick like substitution, like solving linear equations thing to, and you can compare endoscopic expansions. You substitute this SH equals IH thing. And what you get is that IG2 of the pseudo coefficient with this thing away from infinity. You get an IG2 on the compact form, and you're subtracting IHs on this SL2 cross SL2 mod plus or minus 1. And so this is the exact formula that endoscopy gives us. And you can see here, all of these are Euler-Poincare functions, so they're very nice things. Okay. So this should resolve issue 1. Are there any questions? Okay, so now we need to worry about actually computing each of these terms. So first, let's talk about how we might compute this IG2 compact. Right, so spectrally what this is doing is this is counting algebraic modular forms on G2 compact of weight k minus 2 times beta on level 1. And well, again, you write vk minus 2 times beta as the finite dimensional representation with that weight. And we can show that this is just the dimension of the fixed vectors in here. And this dimension, again, there's that formula to compute it explicitly. There's also a table on Gaetan's website that does this up to 50, and there's some computer code that you can plug this in. So there's a table, and you just know what this number is. Okay. So all that's left is dealing with these IH terms. So there are 2 steps to do that. The first step is we need to compute what these actual transfers are. So, I mean, here's just what the transfers turn out to be. The transfers of these pseudo coefficient turns out to be this specific linear combination of Euler-Poincare functions on H. The transfer of this Euler-Poincare function on G2 compact to H turns out to be this other specific linear combination of Euler-Poincare functions. There's an explicit formula for this in some notes of LibS for a very old Snowbird conference. And the hardest part in that formula is figuring out these plus or minus signs. And there are lots of choices that depend on which positive vowel chambers for like K and G2 you use that sort of cancel out in your finite answer and up to, and secretly all that, it depends on some choice of Whittaker models. But there's some tricks you can use to sort of understand these plus or minus signs without too much difficulty. Basically what you can do is if this pi k was the generic discrete series in the packet for a given choice of Whittaker models, then you know that all these signs are positive, and the LibS formula, it tells you how the signs change between different discrete series. So you play those 2 against each other and you can get the exact signs here. Yeah, but in the end, this is just some formula that you need to compute. Then after that, we need to compute terms of the form IH with an Euler-Poincare function. So you just expand it, it's linear. So you have terms like this. So what is this doing? Spectrally, this is counting level 1 discrete automorphic representations of a given weight on H. And the main idea is that H is, remember, SL2 cross SL2 mod plus or minus 1. So up to center, this is the same as GL2 cross GL2. So what you should expect is counting discrete automorphic representations here should be approximately the same as counting pairs of classical modular forms. And here's a lemma that this approximate idea is exactly true as long as you're looking only at level 1. And you can prove this through, again, various techniques of Chenevier, Renard, and Taïbi that apply to level 1. And they used it to do things on classical groups, but the techniques are more general. So they give us that the center issue does not matter at level 1. And that finally gives you the H, the IH terms, and then you have the full formula. So that finishes the argument. Okay, let me just go back to the table. Maybe that's the nicest thing to look at if, yeah, but anyway, does anyone, I guess, yeah, I'm done now. So.